In this lesson, we're going to be looking at an introduction to a new function type called quadratic functions. One of the earliest examples of human beings reasoning about what would eventually be classified as quadratic functions is doing area models. So actually measuring area of land for splitting that land up among people. And so we're going to take a look at the introduction to quadratic functions through this notion of area, and particularly area of a square. So there's an applet that early in this first lesson we ask you to interact with, which is to imagine varying the length of the side of a square and to think about what happens to the area measured in square units. And so you can interact with this applet and you can see different coordinated pairs of values for the side length and the area, the side length being in units, the area being in square units. You're also able to see what the graph of this relationship looks like. And you might at first glance take a look at this and go, this looks like an awful lot like the type of behavior we saw with exponential functions. Now we're essentially exploring this relationship. F of s is equal to s squared, right? Where f of s are values of a. So the area as s increases can be organized in a number of ways. So we saw it in a graph, we saw it through the applet. We can create a table of values. So let's create a quick table of values. When the side length is 0 units, we don't have any area. We're not enclosing anything. We just basically have a point. As s increases to 1, we end up with a square that's 1 unit by 1 unit. Its area is 1 square unit. If we increase that to a 2 by 2 square, the area increases to 4 square units. If we increase it by 1 more, so we go to a 3 by 3 square, the area increases to 9 square units, and so forth and so on. Right? It's pretty obvious. We have just basically a table of values of perfect squares here. Let's think about this change in s over here. Right? So we keep increasing the side lengths by 1 unit at a time. Now, if this were an exponential function, the ratio of consecutive area values would always be the same, right? We'd have a constant growth factor. Do we have that here? Well, if we compare the area here, 1 compared to 0, well, that's actually undefined. Right? So let's check the next pair. 4 compared to 1. So we end up with a multiplier by 4 here. The next one, 9 divided by 4. Well, that's 2.25. And so what we see is this is not exponential. Right? We don't have a constant growth factor. Again, that's because this is a quadratic function. Quadratic functions have a different behavior. They're not linear functions. They don't have a constant rate of change. They're not exponential functions. They don't have a constant growth factor. They have something else going on. So what's going on here? Well, let's go out here in our table and let's think about what the change in A is. How much does our area change? So when S changes by 1 early on, right, area increases by 1 square unit. Then the area increases by 3 square units, and then 5, and then 7, and then 9. And so this is just differences of consecutive A values. Now, if these numbers were the same, we'd have a linear function, right? Because we look at the ratio of those values compared to the change in S, we would always get a constant number. Those values aren't constant, so this is not a linear function. But you might notice there's a pattern in how the area itself changes. So the area first increases by 1, then it increases by 3, then it increases by 5, and then by 7, and then by 9. So we end up with a whole nother column out here, the change in delta A. So how much does the change in area itself changes? Now, say that statement to yourself because it's kind of a mouthful. This column here is how much the change in the area itself changes. And so if we look at that value out here, the change in the area goes from increasing 1 square unit to increasing 3 square units. That itself is a change of 2. We go from increasing by 3 square units to increasing by 5 square units. That is an increase of 2. And so on and so forth. When this column, this change in the delta values is constant, right? That is what makes a function quadratic. That's the key idea about quadratic functions. These what we call second differences. So not the differences in the consecutive y values, but the second differences, the differences in those changes. When that's constant, you get a quadratic function. Now in this area context, we can actually sort of see where this behavior comes from, why we get this. So when we went from a 0, 0, 0 by 0, to a 1 by 1 square, right? We increased by 1 square unit, right? We went from 0 to 1, we increased by 1 square unit. When we went from a 1 by 1 to a 2 by 2, so the length of the side went from 1 to 2, look at what we did. We added these 3 square units. Right? We added those 3 square units. We went from a 2 by 2 to a 3 by 3, so the sides were 3 units long. We added these 5 square units. Added those 5 square units, and so on. You're going to be able to get 7 in the next one. But where does this 2 come from that's in the final column, in the third column? Well, let's think about, for example, as we go from a 2 by 2 to a 3 by 3. So in the 2 by 2, we had 4 square units. We had added these 3 square units, right? We were plus 3 square units from the previous one. Well, we have those added 3 again, plus these extra little boxes on the corner. So we have the increase of 3 units from here to here. We have the increase of 3 square units from here to here, plus these corner points. So a total of plus 5. But those 2 corners are the 2. Then as we go into the next box, we again have essentially exactly how much we got added before. We've got 5 square units, just like we added before, plus these extra corners. So those extra 2 that we kept getting, we keep getting these extra corner pieces above and beyond what we increased before for the area. That's where these 2's come from. And so in the lesson, you'll see the table of values that looks a lot like what we just did, right? So we have these 2 middle columns. These are the side lengths compared to the areas, right? 0 and 0, 1 and 1, 2 and 2 squared, 3 and 3 squared, 4 and 4 squared, 5 and 5 squared, 6 and 6 squared, and so forth. So these 2 are like your normal, table of values that you're looking at, comparing S and A. This column off to the left is showing you changes in S, right? How much does S change by, right? 1, 1, 1, 1. We keep increasing S by 1. This column here are your delta A's, right? How much does your area change by, right? So this was your, keep writing A. That was your delta S. This is your delta A. So how much does the area increase by? It increases by 1, and then by 3, and then by 5, and then by 7. Each of those is 2 more than what was going on before. These are how much delta A themselves are changing. So we just keep going, right? From 16 to 25, that's a change in area of 9 square units. From 25 to 36, that's a change in area of 11 square units. Again, each of those changes is 2 more than it used to be. And we can see this behavior on the graph as well. All right, so we've got our coordinate points 0, 0, 1, 1, 2, 4, 3, 9, 4, 16, and so forth. If we look at changing S by 1, the area changes by 1. If we change S again by 1, right, so we change S by 1 again, this time the area doesn't change by 1 square unit. The area changes by 3 square units, right? From 1 to 4, that's a change in 3, which was 2 more than it did before. We change S again, change S by 1. The area, this time, doesn't change by 1, it doesn't change by 3, it changes by 5. From 4 to 9, a change of 5, which again is 2 more than what it increased by before. We change S again by 1, the area will again change. But again, not by 1, not by 3, not by 5, but this time by 7. 2 more than it did before. So you can see where all of these numbers in the table come into play in the graph. We can see the middle columns here, which are the actual ordered pairs for the quadratic relationship. We can see the changes in S by just imagining stepping through our domain one unit at a time. The changes in the area is how much the y value changes as we change those x values. Those aren't constant, so we don't have a constant rate of change here. Rather, those changes themselves increase at a constant rate. Right? They increase by constant amounts anytime you change S by 1. So your changes in the delta A this time are constant.